Video, let's discuss the question and answer of the thermodynamics. Classify the following into extensive and intensive property: mass, density, volume, and temperature. So extensive properties are the mass, volume. Intensive properties are the density and temperature. Let's go to the next slide. In the next slide, I am taking one more question. That is, what are spontaneous reaction? So what are spontaneous reaction and non-spontaneous reaction process? Give an example. Spontaneous process are that occur naturally without any external intervention or input of energy. These processes tend to proceed in a particular direction under specific condition. The key characteristic of the spontaneous process is that they lead to decrease in overall Gibbs free energy of the system. If delta G is negative, the process is spontaneous. Example: ice melting at room temperature. When ice is exposed to a temperature above its melting point, it naturally melts and transfers into liquid water. The process occurs spontaneously because it leads to decrease in Gibbs free energy. Formation of rust. When iron is exposed to oxygen and moisture, it gradually oxidizes and forms iron oxide, rust. This process occurs spontaneously as it leads to decrease in Gibbs free energy. Let's take what is non-spontaneous process. So non-spontaneous process means are those that do not occur naturally and require external intervention or input of energy to proceed. These processes have a positive free energy, indicating an increase in Gibbs free energy. The non-spontaneous process cannot occur without the addition of energy from an external source. Example: water boiling below its boiling point. Water normally boils at 100 degrees centigrade at standard pressure. However, if the temperature is below the boiling point, the water will not spontaneously boil. The process requires the addition of heat energy to increase the temperature and initiate boiling. Charging a battery. The process of charging a battery involves the input of electrical energy to reverse the chemical reaction that occur during the discharge. Charging a battery is a non-spontaneous process as it requires external energy to proceed against the natural direction of the cell reaction. Let's take one more question. So explain the calculation of absolute entropy in case of solids. Usually it can be framed for 5 marks or 2 marks question, 5 marks or 4 marks question. So the calculation of absolute entropy in case of solid involves determining the entropy change from a reference state, usually at 0 Kelvin, to the desired temperature. The absolute temperature of the solid depends on the factors such as the number of ways the atoms or molecules in the solid can arrange themselves and the vibrational motion of the particle. The calculation of the absolute entropy for the solids involves 3 main steps. One is establishing a reference state. That since the entropy is a measure of a disorder, it is convenient to establish a reference state at absolute zero temperature, that is 0 Kelvin, where the solid is assumed to be perfectly ordered and minimal vibrational motion. In this state, the entropy is taken to be 0. Consider the vibrational motion. At non-zero temperature, the atoms or molecules in a solid vibrate about their equilibrium position. Vibrational motion contributes to the entropy of the solid. The quantization of vibrational energy can be described by the principle of quantum mechanics. Let's go to the next slide. In the next slide, to calculate the vibrational contribution to entropy, one can use the Einstein or Debye model. The Einstein model assumes that all atoms in the solid vibrate at the same frequency. that means Einstein frequency, and have the same energy. The dB model considers the distribution of vibrational frequency within the solid. In either model, the vibrational entropy can be calculated using the following equation, that is entropy of vibration is equal to R into N into natural logarithm 2 plus N into natural logarithm 1 upon 1 minus C to the exponential power to the minus theta upon T. So here S, S of Yb is the vibrational entropy, R is the natural gas constant, and N is the number of vibrational degrees of freedom, and theta is the characteristic temperature of the model. Model may be Einstein or dB, and T is the absolute temperature. Add contributions from other factors. Okay, in addition to vibrational motion, other factors such as electronic energy level, rotational motion for molecules, and any magnetic contribution may also contribute to the entropy of the solid. These contributions are typically small and may be neglected in many cases. By assuming up the vibrational entropy and other relevant contribution, the absolute entropy of the solid at a given temperature can be calculated. It is important to note that calculating the absolute entropy of a solid can be complex and accurate, often require sophisticated quantum mechanical calculations. I will take one more question. Okay. So define Gibbs free energy. Gibbs free energy, the Gibbs free energy is defined as the difference between the enthalpy and the product of temperature and entropy of a system. It is denoted by G is equal to H minus Ts. The Gibbs free energy is particularly useful for the system at constant temperature and pressure. It represents the maximum useful work that can be obtained from the system and determine the spontaneity of the process. Let's take one more question. Give two examples of the state functions. Entropy, enthalpy, and internal energy are the examples of state function. Let's take one more question. Explain the thermodynamic scale of temperature. The thermodynamic scale of temperature, also known as the Kelvin scale, is a temperature scale based on the laws of thermodynamics. It named after the Scottish physicist William Thomson, first Baron Kelvin, who made the significant contribution to the field of thermodynamics. The Kelvin scale is an absolute temperature scale, which means that its 0 point called absolute zero corresponds to the complete absence of thermal energy. In this scale, temperatures are measured in Kelvin, that is K units. Then the Kelvin scale is related to the Celsius scale by simple linear transformation. The Kelvin value is equal to the Celsius value plus 273.15. For example, water freezes at 0 degrees Celsius centigrade C, which corresponds to 273.15 Kelvin, and water boils at 100 degrees Celsius, which corresponds to 373.15 Kelvin. The Kelvin scale is widely used in scientific and engineering applications, especially in the thermodynamics and physics. So, because it has a several advantages over the Celsius scale, firstly, it aligns to the absolute zero of the temperature, making it suitable for the calculations involving temperature difference and energy conversions. Secondly, it eliminates the need for negative temperature values or the values of the Kelvin scale. Finally, the Kelvin scale is the constant with the ideal gas law thermodynamic equations. Let's go to the next slide. In the next slide, I'll take one more question. So give the statement of second law of thermodynamics. So it is impossible for a cyclic process to take heat from a cold reservoir and convert into a work without the same time transferring heat from hot to cold reservoir. It is impossible to conduct a machine which is able to convey heat to a cyclic process from one reservoir at a lower temperature to another at a higher temperature unless work is done on the machine by some outside agency. Entropy of the universe remains constant in a reversible process, but it increases in reversible or spontaneous process. But entropy of the universe never decreases. All naturally occurring processes always tend to change spontaneously in the direction which would lead to equilibrium. Let, let me take one more question. What are isothermal and adiabatic process? A process is said to be isothermal if the temperature of the system remains constant during which each of the process. A process is said to be adiabatic if no heat enters or leaves the system during any step of the process. Let's take one more question. So now give reason even at 0 Kelvin the entropy of the crystalline carbon monoxide is not zero. The third law of thermodynamics states that entropy of a perfectly crystalline substance at absolute zero is zero. However, crystalline carbon monoxide is not a perfectly crystalline substance. It contains defects such as vacancies and interstitial atoms, which gives it to a non-zero entropy even at 0 Kelvin. The residual entropy of the CO molecule is 3.4 joule per Kelvin per mole at 0 Kelvin. This implies that CO molecule does not have perfectly arrangement of the CO molecule. We can say that in a crystalline state, its arrangement like CO, CO, CO and OC, CO, CO, OC may not have a significantly energy difference. That is, carbon monoxide has more than one arrangement is possible at 0 Kelvin. The number of microstates is more than 1, so the entropy is not 0. Let's take one more question. Explain the molecular interpretation of the entropy. The molecular interpretation of the entropy connects the concept of entropy in microscopic behavior and arrangements of the molecules in a system. It provides insight into how the disorder or randomness of a system arises at the molecular level. Energy can be related to the number of microstates available to a system. In this context, a microstate refers to a specific arrangement of the configuration of the individual molecule or particles in a system. A microstate, on the other hand, represents a specific set of microscopic properties of the system, such as temperature, pressure, and volume. As the system temperature increases, the kinetic energy of the molecules also increases, allowing them to explore a greater number of possible microstates. A higher number of microstates means more ways for the system to distribute its energy and particles among different molecular arrangement. Consider a simple example of a gas in a container at a low temperature. The gas molecules have a lower kinetic energy and are confined to a lower possible position and velocities, resulting in fewer microstates. As the temperature increases, the molecular gain more kinetic energy and can occupy greater vary of position and velocities, leading to a larger number of microstates. So every entropy can be thought of a measure of the multiplicity microstates that corresponds to a given macrostate. A macrostate with a higher number of corresponding microstates have higher entropy. This is because there are more ways for the molecules to arrange themselves while still satisfying the macroscopic properties of the system. Additionally, the molecular interpretation of energy is related to the concept of probability. Entropy is a proportional to the logarithm of the number of microstates, and this logarithmic relationship arises due to the uh, probiotic nature of the molecular behavior. The more microstates there are, the more equally probably the system is to be any one particular microstate. In summary, the molecular interpretation of the energy concepts, the macroscopic concept of entropy to the microscopic behavior of molecules in a system. It involves the number of microstates available to the system, the distribution of the molecular arrangements, and the probabilistic nature of molecular behavior. Understanding the molecular interpretation of the entropy provides a deeper understanding of the relationship between the disorder, randomness, the behavior of the molecules in a system. Let's take the one more question. State third law of thermodynamics, the entropy of a pure crystalline solids may be taken as a zero at absolute zero temperature. Every substance has a finite positive entropy, but at the absolute zero temperature, the entropy may become zero. Thus, so in case of pure crystalline substance. Let's take one more question. So derive Gibbs-Helmholtz equation. Here consider free energy G is equal to H minus Ts and H is equal to U plus PV, where G is the Gibbs free energy, H is equal to enthalpy, U will be the internal energy, S will be the entropy, T will be the temperature, P will be the pressure, and V will be the volume. Differentiate above equation, then we will get dg is equal to delta dh minus t ds minus s dt. We know that the value for the delta h, is equal to du plus pdv plus vdp. So substituting the delta h value in this equation, we will get that dg is equal to du plus pdv plus vdp minus tds minus sdt. This will be called as equation 1. For the reversible process, q reversible is equal to t delta t ds from first law of thermodynamics. Then internal energy is equal to q of reversible, q of work of reversible. This will be equation 2. If the work done is only the mathematically, then mechanically, then W is equal to minus PdV. Substituting this value of W in the above equation 2, then we will get du minus q of reversible plus pdv, that is equal to 0. Substituting this value in the equation 1, we will get delta z is equal to vdp minus sdp. This we will call it as equation 3. The above equation gives the dependence of the free energy on pressure and temperature at constant pressure. dP is equal to 0. Equation 3 becomes delta G is equal to minus S dt. Therefore, small g upon delta G upon delta T at constant pressure is equal to negative entropy. Let's go to the next slide. In the next slide, I'm continuing the derivation. That is, entropy 1, free energy 1 is equal to entropy 1 dt, and free energy 2 is equal to entropy 2 dt, where change in entropy is equal to change in free energy. Then change in free energy is equal to minus change in entropy dt. This is nothing but a d of delta G upon delta T at constant pressure is equal to change in entropy, negative entropy. Thus, in the isothermal process, change in enthalpy is equal to change in free energy is equal to change in enthalpy minus T delta S. Substituting the value of ds from equation 4 in the equation 5, delta G is equal to delta H minus T into delta G upon delta T at constant pressure. This equation is called Gibbs-Helmholtz equation. Let's take one more question. A 2 marks question. State first law of thermodynamics. Give its mathematical form. First law of thermodynamics is stated in various forms. Energy is neither created nor destroyed. Only it converts from one form to another. Or when energy of a particular form disappears, same amount of energy appears in another form. Mathematically, delta U is equal to Q plus W. Delta U is the change in internal system. Q is the heat absorbed by the system. W is the work done on the system. Let's take one more question. So you derive a relationship between Cp and Cv from the first law of thermodynamics. Then first law of thermodynamics is equal to delta Q is equal to delta E plus delta W. Ideal gas equation for 1 mole of a gas is PV is equal to RT. With respect to that specific heat capacity, C is equal to delta Q upon delta T. Rearranging a specific heat equation to get delta Q is equal to Cp delta T. Substituting this equation in first law of thermodynamics, we will get Cp delta T is equal to Cv delta T plus Pv. Then Cp delta T plus is equal to Cv delta T plus R delta T. That is nothing but a Cp minus Cp is equal to Cv plus R. That is nothing but a Cp minus Cv is equal to R. Then it is possible to calculate the free energy provided entropy, temperature, enthalpy values are given. Then I will derive an expression for the work done in an isothermal reversible expansion of an ideal gas. Define Gibbs free energy. Consider 1 mole of an ideal gas enclosed in a cylinder fitted with a frictionless piston. Let A be the area of the cross section of the cylinder. The gas is allowed to expand isothermally under pressure P. Let the piston move by a distance dl and reach equilibrium. The small amount of the work done by the gas during the expansion dW is equal to minus force into distance, that is equal to minus P into A into dl. dW is equal to minus P dV, that will be equation 1. The total work done by the gas is obtained by integrating equation 1 between the V1 and V2. Then integration dW is equal to V1 V2 P dV, W is equal to V1 V2 P RT upon V dV. Then W is equal to minus RT integration V1 to V2 delta V upon V. Then W differentiation of this one will get W is equal to minus RT logarithm of V2 upon V1, that is W is equal to minus 2.393 RT log of base 10 V2 upon V1 per 1 mole of a gas. This is the maximum work done during the isothermal expansion of ideal gas. Then define Gibbs free energy. The Gibbs free energy is defined as the difference between the enthalpy and the product of temperature and entropy of the system. It is denoted by G. Let's take one more question. Suppose it is possible to calculate the entropy using this activation energy using this equation, provided two rate constant and the two temperatures are given. It is possible to calculate the activation energy. That's about the question and answer discussion of the